Okay, so welcome back. And can everyone hear me? Would you say yes if you can hear me? Okay, so thank you very much. So we are in the middle of discussing compactness theorem for first order logic. Okay, and as I said, compactness theorem is regarded as one of the most important theorems about logic, especially by the people who study so-called model theory. And then the theorem statement of the theorem was the one that you see on the screen, which says that S is let S be the countably infinite set of first order sentences. So sentence means sentence here means that first order logic formulas without any free variables, And then if that's the case, then this theorem said S is satisfiable. That is, there exists some structure A that satisfies all the formula in this set S, if and only if every finite subset of S is satisfiable. Okay, and then we said the obvious direction of this theorem is this direction, because if we have a structure A that satisfies all the sentences for all F in S, so then then this same structure A will be the one which satisfies every finite subset of S. Okay, and the sentence every finite subset of S. So this is an obvious direction. But so less obvious direction, or something where this theorem says something interesting, is the opposite direction. So this is the non-obvious, and in a sense, this is a direction which is useful for us. And the theorem, the proof of the theorem is what you see on the screen, which I explained the last time. And so here's a quick reminder about how the theorem works. Roughly speaking, the overall skeleton of the theorem is to reduce this compactness theorem into the statement in propositional logic and use the compactness theorem in propositional logic and get it back. And during the reduction, we use Herbrand theorem. Okay, so that was roughly the overall structure of this theorem. And then here's the reminder of how the theorem works. So also we use the parallel scolamizations. So given countably infinite set of formula S, we scolamize all these formulas in countable infinite set of S into some other first order logic formulas. Okay, when we do scolamization, we have to respect this condition of the parallel scolamization, which say that for every sentence, scolam function that we introduce has to be different. So for every sentence in S, we use a different scolam function when we do the scolamization. So if you do so, then what's gonna be true is that for every, if you do so, then what we have is that if for every finite subset, the subset is satisfied if and only if the corresponding subset in S is satisfiable. So the scolamization preserves satisfiability. So that's what we're gonna use in this derivation. Step number 1 to 2, step 5 to 6. These are the places where we use, we didn't really deal with exactly in this form, but we used some property which is similar to parallel scolamization. Which says that this parallel scolamization preserve and reflects the satisfiability. So that's going 1 to 2 and 5 to 6 is okay. And so from the assumption that we have is a finite subset, every finite subset of S is satisfiable. We derive that every finite subset of T is satisfiable by doing this parallel scolamization. And for every finite subset of a T is satisfiable, this E is an Herbrand expansion of every formula in every sentence in T. So I mean, T will contain sentence F1, F2, and so on. And we're gonna do Hurban expansion of the F1, which will be an infinite set typically. We'll do a Hurban expansion of F2, which will be another infinite set, and so on. And then we will define so we will define Hurban expansion of entire T. Sorry, this. So we will define Hurban expansion of entire T to be the union of these guys. Okay. So, and then by the Hurban theorem, we can show, we can argue that this every finite subset of E, this Hurban expansion is going to be satisfiable. So we will look at a bit more details about this proof step, but we're going from the from finite subset satisfiability of T to finite subset satisfiability of E is obtained by Hurban theorem, which say that if some first order logic formula is satisfiable, it has a Hurban model. Okay, so then now this is the going from the 3 to 4, which is finite satisfiability of absolute the E to entire satisfiability E. That's the place where we can use the compactness theorem of propositional logic. And going from E to T, this is again part of Hurban theorem, but I mean, it's actually quite obvious because if E is satisfiable, then that tells us we can build a Hurban model for all the which satisfy all the formula in T. So that is an easy direction of Hurban theorem. So this is a bit hard, but difficult direction of Hurban theorem. And then now if T is satisfiable, then because of these parallel scolamizations, then that implies this S is also satisfiable. So that's how the proof is constructed. But one has, so you can kind of see that the proof of this theorem put many things that we learned together, but there are a few extensions of what we have learned so far. The first, now if you look at this set of formula S and set of formula T, okay? So S, even though S start with consists of all the formulas, all the sentences over structure sigma. Okay, so suppose that structure sigma only uses in the finite number of constant symbols and finite number of function symbols. So it has a finitely many. It doesn't have to be, but suppose it have a finitely many constants, symbols, and function symbols. But if we do scolamization, we will have to introduce function new constants or new scolam constant or new scolam function symbols for each sentence in S, which means that typically for all the formulas in T will be over some sigma prime, which is an extension of sigma, but that will typically contain countably infinitely many infinite number of constants and function symbols. So the reason I'm talking about this is because so far, although we never explicitly say signature is finite in the sense that the number of constant symbols, function symbol has to be finite, we never said that's the part of the requirement. Okay, but all the example we talked about, they assume that the constant symbols and the function symbol in sigma is there are only finitely many of those. But the point I'm making here is that none of the things that we discussed so far depends on that fact. And then, in fact, what's going on in this proof of this compactness theorem is exploiting this extra flexibility we didn't emphasize that much. That flexibility is this signature sigma can contain infinitely many constant symbols and function symbols, and semantics and everything that we talk about still works for in that case. So that's a point one. So here, infinity really appears everywhere, especially infinite signature. So the point I'm making is here is that infinite signature is used. The second point I'm making is related to this guy. Okay. So, I mean, we said if we have some one first order logic sentence F1 in Scholar form, if we do the Hilbert expansions, now when we do Hilbert expansion here, the Hilbert expansion should be with respect to sigma prime, which is infinite, okay? Because the sigma prime is an infinite signature, it's gonna be an infinite signature. But, and then, so there's a one infinity that kicks in. Another infinity is instead of just having this E1, we have E1, E2, and so on. We have to put all of these things together. So one might be worried that, I mean, if you are heard about so-called countable infinity and uncountable infinity and so on, you might be worried that, I mean, if we do so, maybe we are not having so countably infinite, that this E that we obtain, maybe more than countable, it is maybe uncountable set. And actually that's not the case. That's because if you, even though sigma prime is countable, if you do the Hilbert expansion, it will remain countable. Countable union of countable set is also countable. So countability works reasonably well with countable union and so on. So it's not going to cause any other issues at all. Okay, so if you just get confused about what I'm saying, you can just take my words and say things are all working out fine. But if you are more careful about the countable infinity and so on, I mean, here's, we are exploiting some properties of a countable infinite set. Okay. Right. No, there is no uncountable signature. Actually, model theory, we can, people use uncountable signature as well. But our proof of this compactness theorem in propositional logic relied on the fact that the set of propositional logic formula is countable. So if you extend it using, say, ultra products or some things, techniques from model theory, things are all work out fine. But just if we want to be consistent with what we learn, I mean, this is just some property we have to use. Okay, so these are some more subtleties that's going on. So more infinities are kicks in everywhere. So here's the next slide actually shows another subtleties that, I mean, one may overlook very easily, which is about this scolemization. Okay, so now suppose, I mean, it all depending on what we mean by function symbols and constant symbols. But suppose that there are fixed, I mean, it's not about, we are not fixing any signature or anything, but suppose that there are countably many function symbols. That may make sense. I mean, if you say the function symbols are just a sequence of English letters, then there are countably many of those. So suppose there are countably many function symbols like F1, F2, and so on. Yeah. But suppose that this set S already used all these function symbols. So then we are in trouble because some assumptions that's made in the scolemization is that whenever it's necessary, we can always generate fresh function symbols or fresh constant symbols to talk to, and then we can use them as a scolem constant or scolem function symbols. But if S already used everything, then we can't really generate something fresh. So what should we do? So this is some of the, if you want to be extremely formal and want to prove everything in, say, automated theorem prover, these are the kind of reasoning that you have to do. So what should they do? then we have to do some tricks. The trick is that we have to rename. So suppose there are the function symbols we have is f1, f2, and so on. And suppose that all of them are already used in our set of formula S. Okay, so we are in trouble because if whenever we want to introduce new constant symbols, it's already there, so we can't really use it. So then one option you can have is that whenever we can rename all these function symbols f1 to something else. So in particular, we rename f1 to f2, f2 to f4, f3 to f6, and so on. And then for every sentences appearing in S, if it uses f1, we rename it f2. If it uses to f2, we rename it f4, and so on. Okay. So we rename them, then all of a sudden, after the renaming, S, we end up with the symbols like f1, f3, f5. They do not really appear in the renamed version, which if I call it S prime, it does not appear in S. Appear in S prime. Okay, so then when we do the scolemization, we can use F1, F3, F5, and so on. I mean, intuitively, this shouldn't cause any issues at all. That's because, I mean, the whole purpose of this symbol F1 and F2, it's just some symbol to represent some function, and F2 is another function symbol, which is potentially different, maybe same or maybe different from F1, but it's just representing another function symbol and so on. So using different symbols shouldn't really matter. And that's actually the case. And you can formally prove that that statement. So I'm not going to go through the details here, but I will encourage you to think about this. This is a bit like, it's not a hard things to prove. It's more about, it will help you to check whether you are really understand all the subtleties about what's really going on here. So after the renaming, the exercise asks you to prove the two things. We say that if every finite subset before renaming is satisfiable, if and only if finite subset S after renaming is satisfiable. And then the same thing for the whole of S. So really, proving this statement will involve if you have, say, some A which satisfies everything in S, then this renamed version, let's call it S prime. We should be able to produce some corresponding A prime such that that's A prime satisfies S prime, and vice versa. If A prime is given, which satisfies S prime, we should be able to create A. And you can actually do it quite easily in both cases. But doing this type of exercise will help you to understand all the subtleties about what's really going on here. Okay, so here's the proof step of the theorem again, but I guess we covered all these things already. And the only thing that I want to point out here, or give you a reminder, is that, so these are the proof step of the compactness theorem for first order logic. So it's exactly what I told you a few minutes ago. And then the key step from 4 to 5, which is sets with if we have a proposition, this sets the Harbin expansion is satisfiable, then we want to come up with a structure which satisfies T, and that can be done by, this construction of Harbin model that's described in the slide. So we say that when you construct this Harbin model, this propositional model is like what I call assignment when we discuss, when I explain the propositional logic. So if we have a propositional model of assignment that satisfies everything in epsilon and everything in E, we can use that model to construct a Harbin model. The way we construct Harbin model is essentially based on this equivalence. Okay, this equivalence that ground term T1 up to Tk is related by P under the Harbin model H, if and only if the propositional, or this assignment for the propositional, satisfying assignment for the propositional logic satisfies this P T1 up to Tk, where we view this P T1 Tk as a single propositional variable. Okay. So nothing very surprising. It's exactly the step that I told you, and this is just one details about how the construction works. Okay, so now what we're gonna do is that we will use these compactness theorems to, we will see the application of this compactness theorem in the two settings. One is, but in both cases, we will use compactness theorem to construct some strange models or strange structure for a set of formula which is less familiar to us. Okay. So here's the one lemma that follows from the compactness theorem. The lemma says the following. Okay. It says that we have a formula F. So we have a formula F. That's a sentence, so it doesn't have any free variable over some signature sigma. Okay. And then what we do know is that formula F has a model of any finite cardinality. So if it has a model an, which means that there exists structure an that satisfies this sentence F. And furthermore, what we know is that the underlying universe of an is exactly number n for every n. Okay. Which means that for F has a finite model of arbitrary size, and for any size. Okay. So if that's the case, we want to show F has a model with an infinite universe. So it's a bit kind of funny theorem, which say if F has all the finite models, so then it should have an infinite model. So how can we prove this theorem? And we can prove theorems using, prove this lemma using compactness theorem. So here's some ingredient which we can use to prove these theorems. So roughly speaking, our idea is we want to apply the compactness theorem, which means that we want to construct. So what's the compactness theorem? Compactness theorem say there exists some S. So proof. What is a plan? We want to construct some S, okay, which will contain a bunch of sentences, F1, F2, and so on. And then the compactness theorem said if finite subset of S is, so every finite subset of S is satisfiable, so that implies entire S is satisfiable, okay? So that's what the compactness theorem tells us. So what we're gonna do is we're using from the assumption of this lemma, we will carefully construct S such a way that from the assumption of this lemma, so from assumptions, we can say for every finite subset of S is satisfiable. So that's what we're gonna do. We will construct S such a way that this assumption implies every finite subset of S is satisfiable. And then we will construct S also such a way that for the conclusion that we can obtain from compactness is entire S is satisfiable. So that's the conclusion that we can obtain from the compactness theorem. So then what we want to have is that we will design S carefully so that this entire S is satisfiable implies F has an infinite model. Okay. So assumption which has F has a every finite model will imply this set every finite subset of S is satisfiable. And then another property that entire S is satisfiable will imply F has a model with infinite universe. Okay, so that's how we're gonna do. So that means the key step of the proof is really about constructing S. So now how we build S, and then the key part of building S is the one that I described here. We want to introduce a binary predicate, new binary predicate R, and then we will define formula Gn, okay? And what Gn say is that Gn says it consists of two conjuncts. The first conjunct said, well, any x is not related to itself. So sometimes this is called irreflexive. So x is not related to itself. And then second part said we can find n x1 up to xn such that when any xi with a small index is related to xj with a larger index. So I mean is smaller than j. So xi with a smaller index is related to xj with a larger index. In particular, this condition R implies the following. It implies that I mean it implies there had okay, but yeah, Kamal, let me just look at the next. So because R is irreflexive, it doesn't relate X to itself. If we have some situation like this, so you have x1 up to xn, where xi with a smaller index, like xi, is related to xj with a larger index by R, R will never relate same thing. So that implies xi has to be different from xj. So this is a way to encode. We have n different elements. So Gn is a way to encode our structure should have at least n elements. So in fact, you can prove if we have some structure B which satisfies Gn, that implies underlying universe of this B should have at least n elements. Now using Gn to construct appropriate S. So that's going to, that's going to be the proof of this lemma. So I will give you maybe 3 minutes to, or maybe 5 minutes to construct S and then complete the proof of this lemma. Okay, so let me tell you how to prove this. The proof is quite simple. So if you, so here we construct S as follows. We take F and conjoin it with G1, F conjoin it with G2, and so on. So this is our this is going to be our infinite set S. So then for any finite subset, so S0 is say any finite subset of S. So then we can always find the largest n such that f and gn is in S0. I mean, for any S0, because it's finite, then we can really find the largest, the formula, largest sentence of this form with where the index of G is the largest. So that's what we picked here. And we have to check if, then what we know is that because F is satisfiable for any finite model of arbitrary size, and we know that this guy is satisfied by some, so this is satisfiable by some structure. So there exists some structure A such that A satisfies F and Gn. And if A satisfies F and Gn, that's going to satisfy every formula in S0. Because all the other formula were of the form F and Gm, where m is smaller than n. And then this Gm just say there are, the meaning of Gm is really saying there are at least m elements in the underlying universe. So A will satisfy S0. And now by using compactness theorem, so here are some subtleties that I didn't quite explain. Although the original formula is over the signature sigma, but this combination is over signature sigma together with this extra relation symbol R. Okay, so our structure will be over sigma together with this extra relation R, relation symbol R. And then I'm just saying this A, if A satisfies F and Gn, then this A satisfies everything in S0, where we understand A as a structure over this extended signature. Okay. So then by compactness theorem, there exists some structure A such that A satisfies everything in S. But in order for A to satisfy everything in S, so if A satisfies everything in S, then this first implies A satisfies F, because for any formula in any sentence in S, it's always a conjunction of F and something. So A has to satisfy F. Second, because A satisfies Gn for any n, the Gn essentially say the underlying universe of A should have at least n elements. A should be infinite. The underlying universe of A should be infinite. So of A should be infinite. So that's how we can conclude the proof of this theorem. And then the key step, as I said, in this proof is really about the construction of S. And then once you construct good S, then just applying the compactness theorem, we can obtain the kind of property that we care about, the kind of things that we want to get. Okay, so this is some simple exercise, but here's something more serious exercise. So which is about the piano arithmetic. So I mean, one of the things that people studied a lot when, I mean, around the 1900 by mathematician is the axiomatization of number theory. So they thought this number theory is perhaps based on very nice set of axioms, and it's also quite nice. So it should be possible to come up with good, I mean, to encode entire number theory using logics and make sure we never make, I mean, mathematicians never use inconsistent rules or contradictory reasoning steps. Okay, so that's what they wanted to do. And then there are many mathematicians who try to formalize the number theory. Okay, so when they try to formalize number theory, I mean, what remains nowadays, there are two very famous axiomatization of number theory which remains and which actually is used by computers when they reason about programs automatically. So the automated theorem prover or SMT solver often use the either piano arithmetic, not SMT solver, but automated theorem prover often use the piano axioms that we're gonna cover now, or Pressburger arithmetic, which is something a bit simpler than this one, but less powerful. But in both cases, this is all based on some formalizing the number theory using this signature. I mean, not all, but this piano, especially piano axiom is based on this signature, which have the following symbols. So this is an axiomatization of a formalization of number theory. So it have a constant symbol 0. And then it has three function symbols. The first is the S is a successor, or if you're more familiar with computer science, the S is like increment operations. So if you give an integer 3, in return, intended meaning of S is in return number 4. Plus means plus. I mean, this dot means multiplications. So this is an additions. This is a multiplication. And then we have an equality symbol. Okay, so this is the signature which we can use to formalize the number theory. And then typical model of this is, sigma is going to be some model that we are familiar with. So here we said this is a standard structure on N, or sometimes it's called classical arithmetic. So this refers to a particular structure over this signature sigma. And then particular structure is what you are used to. So underlying universe in this case is going to be the set of non-negative integers. So for computer scientists as well as logicians, I think we consider natural numbers starting from 0. So it's just natural numbers starting from 0. And successor is really increment operation. And then plus really means mathematical plus. Multiplication really means mathematical multiplication. Equality is a binary relation, which say two things are equal if and only if they are really the same. So this is a structure that's called classical arithmetic. Okay. Now the question becomes, some mathematicians, or maybe we want to ask right now, is that can we come up with set of the first order logic formula such a way that any model that satisfies all those this is the set of first order logic formula or first order logic sentences, more precisely, a set of first order logic sentences can be infinite, so that's not a problem. So we want to come up with set of infinite set of formulas, S. But what we want to do is we want to come up with S such a way that whenever we have a model, or we have a structure which satisfies every formula in S, we want that this A is isomorphic to, and let's call this A as a standard, isomorphic to AST. So what does isomorphy means? Isomorphy means that there is a bijection between underlying universe of A and underlying universe of AS is standard model for arithmetic. U of AST. And then this modular, this bijection, this A and AST say exactly the same. I mean, bijection is nothing but just renaming of all the elements in A. So if you do the renaming, the function, what functions, the interpretation of function symbol in A, interpretation of function symbol in AST, they are exactly the same, and so on. So that's what we mean by this isomorphism. So the question is, can we somehow come up with axiomatization, which can potentially use infinitely many formulas in such a way that any structure that satisfies the infinite set of formula or infinite set of sentences looks exactly the same. So that's the question that we want to answer. And then piano, in a sense, provide the piano axioms. You can view this as an attempt to answer this question. So piano, I'm not sure whether he did it or maybe some other people did it later, but what's called piano axiom is an attempt to define this as set S, which characterize so this attempt to define S, which try to characterize this classical arithmetic, was the standard notion of net set of natural numbers, increment, plus, and the multiplication. Actually, there has to be number 0 here. Okay, before moving on, let me just say a few words about this guy, the Giuseppe Peano. I mean, he was a famous logician and a set theory and mathematicians around 1900. And he made many contributions in logic and mathematics. But another interesting thing he did was he was very much interested in artificial language. So he wanted to design his own language. Especially, he spent quite a bit of his energy to design a simplified version of Latin. So I heard in Latins, there are some verb change in a very complicated way. He wanted to remove some of these complications. So I think that when there was this mathematical conference, this international conference on mathematics, which is a very famous conference in the world. When that happens in some year, like around the beginning of 1900, that means maybe a few days before, a few days later, there was a very similar conference for philosopher or linguist. And then this Peano attended this, I mean, both of them were, at least he attended one and his students attended one for mathematics. But later when he gave talks on his artificial language, which is a simplified version of Latin, I heard that when he gave talks, initially he started with the Latin. That was the official language at the time. But whenever he explained the simplified version of Latin, he changed his language so that after introducing, say, for instance, it's a bit like if introducing universal quantification, he started to use this universal quantification in his language. He changed the language of his speech according to what he presented. So at the end, he only speaks based on the language that he's presenting in the conference. That's what I heard. Very interesting person. But one of the key figures in the foundations of logic. Okay. So a Peano axioms is not very old-fashioned. It's still used quite a lot. I mean, it forms a basis when people talk about axiomatization of number theory. This is often the one that people use. So Peano axioms is very simple. It consists of 6 axioms and 1 axiom. And when I don't know how to call it, some like induction principle, but the basic 6 axioms are like this one. So it says that the first one says for every x, successor of x is different from 0. So if you apply the successor, you get something always different from 0. The second says successor function is injective. So if you get successor of x and successor of y is the same, then x and y is the same. So successor is an injective function so these two together say successor is an injective function whose image doesn't really contain 0. And then the next two is about axiomatization of 0. So you can think of this as, I mean, if you want to implement additions, then this is the kind of things that you're gonna do. So you say, this is the first talk about base case. So if it's the second, what we add in the second argument is 0, x plus 0 is x. Otherwise, we recursively compute x plus y and add the successor. And the next fourth and the fifth and the sixth axioms, axiomatization of multiplication, defined very similar way. Multiplying with the 0 is a 0. Otherwise, we recursively compute x times y and then just plus x. Okay. So, I mean, based on your understanding, then these are the, in a sense, obvious facts. So, I mean, obvious fact means it's actually, if it's good enough, that's a very good actions. Now, piano axioms have these 6 axioms together with one more that captures induction principle. And this is a direct encoding of induction principle in actually a second order logic, not the first order logic that we are talking about. So induction principle said, what is the induction principle? Induction principle said, if we show, I mean, 0 satisfies the case, and then assuming something is true, it is also true for k. Is true for k. If it's true for, I mean, true for x. If it's true for x plus 1, then that has to be true everywhere. So that's the induction principle. And induction principle can be understood as some reasoning principle about set. So you say that, so this is an encoding of induction principle using the second order logic. Is that for every set of integers, if that set contains a 0, and then the set has some closure property with respect to successor. So if x is in the set, x plus 1 is in the set. So S of x is really x plus 1, and x plus 1 is in the set. That means this set y should contain all the natural numbers. Okay, so this is really an encoding of induction principle in second order logic. But in first order logic, we have to do something a bit different because we don't have quantification over sets. So here's a, so instead of having only one formula, we have a countably infinite set of formulas which captures this induction principle. So that induction principle say, for any formula phi, so it's not a sentence, it's a formula, so it can have a free variables, but its free variables are all, I mean, one of x, it's all covered by x and y1 up to yk. So x, y1 up to yk are all the free variable and possibly more inside the formula phi, okay? And then we are saying for any y1 up to yk, so if we fix y1 up to yk to arbitrary value, then we can now think about whether phi is true for all the natural numbers whenever, so for every x, so that's what we want to argue. And to do so, this theorem, this formula say you have to show the following, which is if you show that p of 0 is true. So this is an abbreviations, which is really by expand everything 0 and y1 up to yk. But because y1 up to yk are fixed, and then just to simplify the presentations, it's just written a p of 0. And so p of 0 is true, and then for any natural number, p of, if assuming p of x, so this is again y1 to yk, and this is p of s of x, y1 to yk. So if assuming p of x is true, if we can show p of s of x is true, then the p of x is true for every x. So that's what this theorem is. I mean, this formula is telling us, and this formula actually captures induction principle for specific formula phi. And because we want to say induction holds for every property, and we want to include this type of formula for every, I mean, for every formula phi in this first order logic signature. Okay, so that the right, so the axiomatizations of the number system in piano arithmetic is the union of all those formula, the 6 formula above, or 6 sentences above, and then the sentence that I just described for every possible fit. Okay, and this is sometimes called so this is a piano actions, and then classical arithmetic, so specific structure that I showed you based on our usual notion of natural numbers is a model of this set of formulas. Okay. So now what we want to do. So what we want to do is we want to construct some non-standard model of this piano axioms. So I will call this S of PA as a piano axioms. We want to construct non-standard model of piano axioms, which means that it's a very strange structure, which is not quite isomorphic to our usual notion of set of natural numbers, non-negative integers. But it will satisfy, the first order logic sentences that we collected in S of PA will never distinguish it. All the formula will be true there. Okay. And to do so, we're going to use this theorem for compactness theorem, which we didn't quite prove, but this compactness theorem for first order logics is true even when we include the notion of equality. Okay. So we're going to use this to prove this these things, which is this S of PA, piano axioms, has a model not isomorphic to the classical arithmetic. So here's how we do it. So the proof about doing this is very much like the one that we see before. Okay. So what's the goal? Okay, let me just write it. So what's the situation? This is a piano. Use a blue. This S of PA is piano axioms, which has an infinite set of formulas, and which looks reasonable. And in fact, this actually covers quite a bit of what people do in the, in the number theory. Then we have models of this, which we call it classic arithmetic. This refers to a structure, I'll call it standards, whose underlying universe is a set of natural numbers. And then 0 means 0, successor means +1, usual successor, and usual plus, multiplication, usual notion of equality. And this is exactly what you have in mind whenever we talk about the set of natural numbers. Okay, but our goal is we want to construct some structure, A prime, which is not isomorphic to this guy, but still satisfies all the formulas in the all the piano actions. But SPA. So this type of A prime is what we are looking for. Okay, so how should we do this? And we're gonna use a compactness theorem. So we will, what's the general plan? General plan is using all the data that we are given here. The data is, we are given S of PA. So we are also know that this A of ST. Then we're gonna construct some set of formula S from here. And then using this, the fact that A of this is the classic arithmetic satisfies every piano axiom, we will deduce that this S, every finite subset is satisfiable. So then by compactness theorem, we say entire S is satisfiable. This is a bit weird word, but it's satisfiable. The entire set of S is satisfiable. And from there, we will construct A prime. So that's the general plan. And here we are using compactness theorem. So then question, the general plan of this, for the instantiation of this proof, the key step is to defining this S. So here's how to construct this S. So to construct S, we're gonna consider, this is a set of formula C. Okay, so this set of formulas is of the form. First, we will pick a fresh constant symbol C. So this C, this constant C is something that doesn't really appear in the signature. So it's just some fresh constant symbol C. And then we will consider the set of following formulas, which is an infinite set. And this is C set, this Carly C, this guy consists is an infinite set of formula which said this constant C is different from 0, C is different from S of 0, C is different from S2 of 0, and so on. So if we expand this to really say C is different from 0, second one say C is different from S of 0, and C is different from S2 of 0. S2 means applying S twice. So altogether, what does that mean is that C is something which we can't really obtain by applying this successor function to 0. Because it's different from 0, different from 1, different from 2, and so on. So C is something which is different from any of the usual natural numbers that you can construct from 0 and successor. Okay. So that's what this C is telling us. But now if you put these S of P, A, and C together, then that's gonna be a countable infinite set. This S of PA is a piano actions. And then none of them, by the way, okay. So none of them will refer to C. Because the C is something that we choose, is a fresh symbol. C is not appearing there, okay? And then the symbol C is not appearing. This curly C, or this capital C, is a really formula that we just constructed, which really talk about C is different from any SI of 0. Okay. So, but because S of PA and C, both of them are countable, if you put them together, that's a countable. And then one thing that we know is any finite subset of this guy is satisfiable. Okay. Why that is the case? The reason is if you take any finite subset of SPA union C, okay, it's called finite subset S0. And now we take this standard mod, this classic arithmetic, AST. I'm claiming this AST satisfies the finite subset S0. So this finite subset will consist of S01 union S02. And S01 is really coming from, it's a subset of the S of PA. So it all consists of piano actions. S02 consists of is a subset of this capital C. Okay. So then the classic arithmetic will satisfy this S0 superscript 1 because our classic arithmetic satisfy every formula, every piano actions. This is okay because AST satisfies this entire piano action. But now the one remaining part is this one. And that is also okay because S02 is finite, which means that we can find we can find the maximum I such that the CSI 0 is in S02. Okay, so because it's finite and everything in S02 will of this form, not C equal SI 0. So if you just pick the maximum index I, we can always find the maximum index I. So what does that mean? That means if we pick, so let's say I is say 20. So if you pick map C to be 21, no, maybe 23, then I mean, this will be the interpretations of which will satisfy the every formula inside S0 superscript 2. Because I mean, S0 superscript 2 only says C is different from 0, different from 1, up to different from 20, maybe 20. So if you map C to 21 or 20 to 23, then that will still satisfy the every formula in S02. Okay, so this S02, we can find I. So then, I think actually I was not quite right. So what we have to do is we have to map this C to maybe I plus 1 here. So then this AST where C map to I plus 1 will satisfy the pure arithmetic. Then AST where C gets mapped to I plus 1 will also satisfy S02. So what's really happening is the C, this capital C, the entire thing is a bit hard to satisfy, but any finite subset is really easy to satisfy because it just say C is different from some numbers up to some point. Okay, so if you just pick C to be a number large enough, then it's very easy to make it true. So now if we show that any finite subset is satisfied by appropriate modifications of the classic arithmetic, which is written here. So then by compactness theorems, we know that so by compactness, we know this entire thing S of SOPA union this call it C is satisfiable. But if SOPA union C is satisfiable, that means it's the constant symbol C. So if you have some structure A that satisfies SOPA union C, then this is in the structure A, this constant C should be mapped to something that mapped things should be different from 0, 1, and so on. Okay, what does that mean? That means this inside the A, its underlying universe of A will consist of the interpretation of 0 is under A, and I will just write it like this. Yeah, interpretation of the successor applied to interpretation of 0 and so on. We can apply I times. Okay. Of 0A, but there are something which is not one of these, which is just the C of A. So that's different from any of these things that can be obtained by applying the successor. So this cannot be, I mean, it can be a bijection, but this cannot be isomorphic to, so this is, let's say that, let me erase this. This says this A cannot be isomorphic to AST, because in AST, every element in the underlying universe can be obtained from 0 by applying the successor. But in A, there are some elements which can't be reached by applying this successor. And the interesting bit is that this A will still satisfy all the piano actions there. Okay, so that's how we can prove this type of theorem. Okay, and then in fact, this is a much more general consequence. So you might kind of, at this point, you might kind of say, oh, that's this whole thing So what's our goal here? Our goal was we are interested in this classic arithmetic, which was called AST, which is the n0 plus, successor plus multiplication equality. So we are interested in this structure. And we want to come up with a potentially infinite set of formula that completely characterize this structure, but we fail because the attempts by Peano, so these Peano axioms. So we just show that there exists some A prime which satisfy these Peano axioms, but that's not isomorphic for AST. So then you might kind of think, oh, that's because this Peano axiom is bad. So this is, maybe we can do, we can change this ASPA and then achieve our goal. And then to something else. And it turns out that's not possible. So there's a more general result, which is called upward Nimes theorem, which says that if you have a set of formula S over a finite structure, so sigma has to be finite, which means that the number of constant symbols, number of function symbols, number of predicate symbols, they all together to be finite, okay? And a set of formula can be infinite. I mean, typically this is a set of sentences. And if a set of sentences over a finite structure has an infinite model, so then it has this set S has an infinite model of arbitrary size. So for any cardinal kappa, so I don't know whether you heard about something called cardinal or ordinal, but obviously I'm going to explain what it is. So this cardinal is a measure of infinity. For any cardinal kappa, this S will have a model whose underlying universe has a cardinality kappa. So for instance, in what this theorem tells us is for this cardinal is a measure of infinity, and then this cardinality can be countable, uncountable, and even larger than uncountable. So what this theorem tells us is that for this SPA, I mean, we have this classic arithmetic, infinite. We have this SPA has an infinite model classic arithmetic. Furthermore, that it's over a finite structure. Well, actually, this is not structure, but it's a signature. It's over finite signature. So we can have a model of these Peano axioms, which is uncountable. So, and that's what this theorem is telling us. And we can even have a model which is larger than uncountable. And that happens for any set of formulas. So that's an upward Nimes theorem. If we have some infinite model, we can create the infinite model of arbitrary size. We can make a model larger and larger. So that's what this upward Nimes theorem says. Because of this, we can't really formally and fully characterize the classic arithmetic using first order logic sentences. And in fact, there are some other important theorem from model theory, which is the opposite, which is called downward Nimes theorem. So upward Nimes theorem say, if you have a model, you can have a larger model of arbitrary size. Now, downward Nimes theorem says the opposite direction. If you have a large model, you can actually have reasonably small model. They are all about infinite models, but upward talk about even larger model. Downward talk about smaller model, especially countable model. So interesting application of this downward theorem is actually axiomatization of set of real numbers. So think about this is sigma as a structure. No, actually it's a signature. Sigma is a signature which contains constant 0, constant 1, plus multiplication less than an equality. And let's collect all the set of, let's think about a structure. So this is a signature. Let's think about specific structure, which is based on a set of real numbers. Okay, so it's a set of real numbers. And then the 0 will be interpreted as the real number 0, 1 will be interpreted real number 1, plus addition of 2 real, multiplication of 2 real, less than of 2 real, equality. And so then we can consider the set. So that what can we do? One thing we can do is that now we collect. So this is a one particular structure. So let's call it R. Structure of this signature. Then we consider all the first order logic formula that's satisfied by this A of R. Okay. This is about first order logic sentences. Sentences over sigma and A R will satisfy F. Because the sentences are all finite, I mean, this S is a countable set, countably infinite set. And we know that this R, A of R, will satisfy S. And by definition, because we just collect all the sentences that's true under A of R. Okay, so it's a, so then we can, so in some sense, we can say this S is a formalization of the set of reals. But it turns out this formalization has a countable model because of this so-called downward Loewe-Nimes-Golem theorem. Downward Loewe-Nimes-Golem theorem said if we are given a set of a formula over finite structure, finite signature, sorry about this, I mean, so if you have a finite signature, and then that finite signature has an infinite model, so then there has to be a countable model. So there has to be a model over all the formulas in S whose underlying universe, the size of the underlying universe is countable. So what does that mean? That means this S, which we constructed by based on our usual notion of set of real numbers. Actually, if you only focus on this S, then there is a structure A prime, okay, that's such that this A prime will satisfy S for every formula in every sentence in S, and at the same time, its underlying universe A prime will be maybe just cardinality is maybe confusing. A prime is countable. So it's a bit weird. That's because, I mean, you think that set of real is uncountable, but whatever you can say about the set of reals, actually you can come up with, in a sense, I mean, the countable version of set of reals, which say exactly the, well, not exactly, actually exactly the same thing as what the set of what you can say based on set of reals. So as far as first order logic formula is concerned, I mean, this A prime and then A of R, they are indistinguishable. So first order logic sentence can't really distinguish these two. So that's upward Loewe-Nimes-Golem theorem say if you have an infinite model, you can have an infinite model of arbitrary size. You can make a model large, bigger, and bigger. Downward Loewe-Nimes-Golem theorem says if you have an infinite model, you can make that model smaller and make it countable. So, and I mean, so this is a consequence that I just told you. That says a model with a countable universe. And I mean, just maybe don't worry too much about not isomorphic to the classic arithmetic part. Okay, so erase this. Okay, so that's it for today. So what we covered today, well, we talk about the compactness theorem for first order logic. And then I showed you how to use the compactness theorem to construct some strange models. The first was an application which said if we have a model of any finite size, then that set of first order sentences should have an infinite model. Okay, if it's finitely satisfiable for any n, then it should be infinitely satisfiable. So that's one thing that we talk about. The second, we talk about the axiomatizations of the arithmetic and the number theory as well as set of real numbers. And then for number theory, I showed you how to use the compactness theorem to construct some non-standard model. Okay, so that's it for today. I'm gonna stay here for about 5 more minutes. So if you have any questions, you can ask me. Next week, we will move on to some decidability result on first order logic.